Hello everyone, in this presentation we are going to discuss about what is a task and task can be in how many states. Okay, so this is a part of real-time operating system from the David E. Simon. The chapter 6.1 talks about task and task states, which is summarized in this Word file as a question and answer for our convenience. Basically, what is a task? A basic building block of a software written under a real-time operating system is a task. A task is simply a subroutine. So whatever work that we are going to do, if you want to make that work to do, a system has to do that work, means we have to write an instruction to that particular system to make that work to happen, which is called as task. The subroutine is a task. A task can be in how many states? Task can be in 3 states. Task can be in the running state, task can be in the ready state, task can be in the blocked state. So when the task can be in the running state, the microcontroller is executing the instruction that makes up this task. One task can be in the running state. So because it is a single processor, one task can be in the running state. And how many tasks can be in the ready state? Some other task is in running state, but this task has something to do if the microcontroller is available. Any number of tasks can be in this state. So what do you mean by ready state? Say for example, whenever when we press a key, right? When we press a key, the key scan subroutine has to work to identify which key I am pressing. Until I press the key, task can be in the blocked state, and when I press the key, task will come to the ready state. Whenever the processor is available, it will go to the running state. That is the way we need to understand. So what is blocked state? This task hasn't got anything to do right now, even if the microprocessor becomes available. Tasks get into the state because they are waiting for some external event. So that they are waiting for external event means if there is a function, the function need not execute unless something happens. Say for example, if you say the fire alarm, the fire alarm should not produce any fire alarm unless otherwise there is a fire. So there is a code written to produce the fire alarm. The code which produces the fire alarm must not execute and need not execute unless otherwise there is a fire. So that code can be in the blocked state. Whenever there is a need, the code will come from blocked state to the ready state. Whenever there is a processor is free, the task will go from ready state to the running state. While running, it will do the job. That's all. Okay, so that is the one we need to understand. So the example here with respect to Simon author book, example 1 here, what is given is a task that handles the data coming from the network will have nothing to do when there is no data. A task that responds to the user when the user presses a button has nothing to do until the user presses the button. Handles the data coming from the network will have nothing to do when there is no data. So any number of tasks can be in the blocked state. Okay, so this is the pictorial representation of task and task states. So task can be in the blocked state, task can be in the ready state, task can be in the running state. Okay, so whenever the task is in need of some processor, it will come from the blocked state to the ready state, right? When whatever the task needs happens. So whenever the task needs happens means it will come to the ready state. Okay, then whenever the processor is available, it will come to the running state, and once the task is over, it will go back from running state to the blocked state once the process is over. If I pressing the key, say for example, until I press the key, it will be in the blocked state. When I press the key, it will come to the ready state, and whenever the processor is available, it will go to the running state, and then it will identify the key press, and then it will store the key press value, or it will display the key press value, and then the task key press task has nothing to do, so it will go to the blocked state, something like that. Okay, so a task can move from ready state to the running state, and then running state to the ready state. Okay, so we will discuss about that soon. Okay, so what is a scheduler? It's very important here. What is a scheduler? The part of the operating systems called a scheduler, which keep track of the state of each task and decides which one task should go into the running state. Scheduler look at the priorities be assigned to the tasks, and among the tasks that are not in the blocked state, the one with the highest priority will runs and the rest of them will be in the ready state. The shuffling of tasks between the ready and the running state is entirely the work of the scheduler. Okay. So what does scheduler do? Scheduler will look after the tasks present in the ready state and running state. N number of tasks can be in the ready state, n number of tasks only one task can be in the running state. Among n number of tasks in the ready state, which task is having highest priority, that will come to the running state. All other tasks with lowest priority will wait in the ready state for the processor. That's all. So among the several tasks in the ready state, the task which has highest priority will come to the running state. So the looking after the ready state and running state is the major task of your scheduler. How does the scheduler know when a task has become blocked or unblocked? This is very interesting question. Okay, scheduler is a part of an operating system, real-time operating system, but the task is the program that the user has written. How this user code notifies the scheduler in the real-time operating system is the question here. So RTOS provides the collection of functions the task can call to tell the scheduler what events they want to wait for and to signal that events have happened. Okay, so there is some procedure. Based on that procedure, if you write the function, then the task can signal the RTOS to notify that it has become unblocked. That's the idea. That is what mentioned here. What happens if all the tasks are blocked? It's a good question, right? If all the tasks are blocked, then the scheduler will spin in some tight loop somewhere inside the RTOS, waiting for something to happen. It is something like a short jump here. Normally in our 8051 programming, if you have nothing to do, then we will wait in the same loop. Short jump here, short jump here, short jump here, short jump here. So it is something like it will be spinning in the same row. So something like jump, short jump here. We have to write the simple code in such a way that if all the tasks are blocked, means RTOS has to make the processor to spin in some particular routine like short jump here. That is what mentioned here. What happens if all the tasks are blocked? If all the tasks are blocked, then the scheduler will spin in some tight loop somewhere inside the RTOS, waiting for something to happen. If nothing ever happens, then it is our fault. We have to write something like short jump, otherwise it will go and do some malfunction. Okay, unless otherwise if you write the short jump here, the program may not work as per our expectation. Okay, it's our responsibility to write a short jump code. Similar to that, in the RTOS we have to make some spinning code. You must make sure that something happens sooner or later by having a interrupt routine that calls some RTOS functions that unblocks a task. Okay, so that is what. What if two tasks with the same priority are ready? What if two tasks with the same priority are ready? So there are several different RTOS which handles this issue in different ways. Some RTOS will not allow two tasks with the same priority. This is one option. Some RTOS will time slice between the two such tasks. This is another option. The third option, some RTOS will run one of them until it blocks and then run the other. It's very interesting, right? So based on the need, we can choose the RTOS and we can make the system to work as per our expectation. Okay, next question. If one task is running and another highest priority task unblocks, does the task that running get stopped and moved to the ready state right away? It's a very interesting question. That's what the term called preemptive comes into picture. So the preemptive RTOS will stop the lowest priority task as soon as the highest priority task unblocks. Okay, so figure 6.3 shows how preemptive RTOS works. Okay, so what is 6.3? Here you can see the lowest priority task is running. Whenever the highest priority task unblocks, it goes to the highest priority task. Once the highest priority task completes its task, then program execution return back to the lowest priority task, and then it continues the lowest priority task. So until the highest priority task unblocks, the lowest priority task will be running. Whenever the highest priority task unblocks, the lowest priority task will come to the ready state, then highest priority task will run. Once the highest priority completes the task, it goes to the blocked state, then the lowest priority task continues to run. So this diagram represents that very clearly. Okay, so the horizontal bar shows that which task is in the running state, and here the button task and levels task. Level task tank level computation will be the lowest priority. Pressing the button is having the highest priority. So until we press the button, calculating the tank level will happen. When the button is pressed, button press is having the highest priority, so button press value, task will get executed. So this is the pictorial representation, which is much more clear for us. Okay, so the non-preemptive RTOS will only take the microprocessor away from the lowest priority task when the task blocks. It's very interesting, right? So 8051 microcontroller is non-preemptive, which is we need to understand, right? 8051 microcontroller is non-preemptive. While timer 0 interrupt service routine is running, external interrupt 0 unblocks. It will never preempt the running timer ISR. This is very important, right? Okay, so because external interrupt 0, even though external interrupt 0 is having highest priority, but timer 0 interrupt service routine is running, but external interrupt 0 unblocks, it will never preempt the running timer 0 ISR, even though the external interrupt 0 is having highest priority, because 8051 is non-preemptive. You cannot interrupt the current interrupt service routine. External interrupt 0 ISR will execute only timer 0 interrupt returns from the interrupt service routine. Hence 8051 is non-preemptive. Okay, this will happen only in the preemptive kind of real-time operating system. Okay, so this is the one which we need to concentrate with respect to the corresponding tasks, and this is the task. Task means a subroutine, and task can be in 3 state: ready state, running state, and blocked state. Thank you.